scale model kit of, it was a 3-pack of models, which was really cool. It was an F-16, an F-117, and a plane I've never heard of before. So it's a pretty cool little model kit, and they're all 1 to 72. Or you can write it like this, as a fraction, 1 over 72. And what this means is that the model that I'm going to build is 1/72nd the size of the actual aircraft. So every single measurement on the model that I'm going to build, or the diagram that you might have in front of you, is proportionally either enlarged or reduced depending on what it is. Obviously, I'm building a plane, so it's going to be smaller than the actual plane. But sometimes in science, you're looking at diagrams of things that are really, really small. DNA, cells, atoms. And these models, Dil Karan, please stop talking, are a whisper. The diagrams you're going to look at are scaled up. The diagram is bigger than the actual. And so, and it's always a multiplier. So proportional means that all measurements are enlarged / shrunk, which is a great word, by the same multiple. So depending on what you're drawing, depending on what you're building, or maybe you're building something based on a scaled down drawing. If you're going to construction, or you work already in construction, you're obviously not going to have a blueprint that is the same size as the building that you're building. That would be a lot of paper unfolded over the ground. It would get ridiculous. And so you have this scaled down drawing so that you could then build out from that. One common use of scale models is to show mini versions of what a building would look like. So it's really hard to tell actually without having these photocopied in color. This is a picture of the actual building on Ware Street. This is that yellow one. It's got like the awkward, it's got awkward yellow balconies and sections of the walls on the outside are yellow. It's in the same, there's a green one in there too, and a blue one and a red one, I think, in the same complex. And this is the scale model. Back when they were designing that complex, to get approval from the city, they would have walked in there with a model and say, this is what we want to do with that property. Oliver and Hayden, stop talking to each other or go to the couches and have your conversation there. Yeah, those are your choices. Then I mark you away and you're not allowed back. So if the scale model or the diagram is smaller, we call this a reduction. I know this isn't overly complex. You've likely heard these words before. If the scale or the diagram is larger, the model or the diagram is larger, we call this an enlargement. And has anyone seen Zoolander? One of you. Is one person, two? A few of you have seen Zoolander? If you've seen Zoolander, this is fantastic. Zoolander doesn't understand that this Zoolander, the Center for Kids Who Don't Learn Good, I think is what it's going to be called. And he walks up there and he says, is this a center for ants? Because he's really supposed to be that dumb. It is obviously, this is not the center for ants. This is a scale model of the Center for the Children. If you've never seen Zoolander, highly recommended. It's as stupid as it sounds. He's a male model who can only turn one way. The big pinnacle of the movie is he learns to turn the other way. They have a gasoline fight at the beginning. It's wild. Great movie. Great movie. I digress. We can also use, and I said it already, we enlarge models in science all the time. This is an animal cell. This is the general shape of the cells that make up you. Obviously, they're not this big. If they were, you'd look like you were covered in marbles. It would be weird. This is a scale, well, it's not probably not to scale, but this is an enlarged model of DNA. If you had science this semester, or you're going to be in science next semester, you will have had done this, or you will do this at some point. That depends on who your science teacher is. But you will build models of DNA. Obviously, these are much larger than actual DNA, because actual DNA is coiled up inside that part of your cell, and these cells are really small. Yes, Dil Karan. Congratulations. Thrilled for you. Flip the page. we can use okay, so there's a typo here. Now, how much shouldn't be there? I smashed two sentences together and they're both wrong. So get rid of that first part. A scale model is described by a scale factor. This scale factor can be given as a fraction, can also be given as a ratio, which we'll look at later. And the scale factor is the multiplier I referred to earlier. Multiply. As you're walking by, Brielle, stop. Yeah, you're going to grab something from the box. Looks like this. No, over here. Over here. Okay. Yes. And Brielle, the attendance question was one positive thing from the last 2 weeks. Excellent. I also enjoyed doing nothing. Okay, so we got our scale factor. To figure out what the scale factor is, the fraction is always set up the same way. It's a scale factor is equal to a length in the scale diagram divided by the same length in the original. So if you have a scale factor between 0 and 1, it means that the numerator here is smaller than the denominator. The numerator is always what it is in the scale. So if a scale factor is between 0 and 1, you're going to have a reduction every time. Because the numerator represents the length in the model. The denominator represents the length in the original. And so if this is between 0 and 1, or it's some fraction, a proper fraction, the scale diagram is smaller. So this is our original. And maybe it's been shrunk down to a toy. It was shrunk. Or maybe you've got a smaller original. Maybe you're looking at a Hot Wheels. Hot Wheels something, I don't know. Hot Wheels makes some ridiculous cars. Maybe you want to take a Hot Wheels car and you want to blow it up. A bone shaker?
Yeah, it's the one car with the engine and the skull at the front.
Yeah.
They made the real life version.
So it was originally a Hot Wheels and they made it a real. So that this is exactly what they've done. They would have taken all of the measurements in that original and they would have scaled it up. They would have made an enlargement. What was it called? Bone Crusher?
Yeah, they have a bunch of them.
Nice.
None of them are couple. All of this size.
So a scale factor, and this would give you, if your model is bigger than the original, you're going to have a larger numerator than denominator. If you have a larger numerator, it means you've got a mixed number or an improper fraction. It means that you're making this thing bigger. It's an enlargement. So like with the example, well, the thing I mentioned right at the beginning with the birthday gift I received, the models that I will be building are the actual version of that aircraft will be 72 times larger, whatever I'm building. In this case, I'll probably start with the F-16 because why not? So if I have a scale factor of 2, what's happening on the diagram? Is the diagram an enlargement or a reduction of the original? The scale factor is 2. It's bigger. It's an enlargement. The diagram is an enlargement of, I'm just going to use the letter E. E for enlarge. And specifically, if it's a scale factor of 2, how much has it been enlarged? It's twice as big, yeah. So the diagram is twice as big as the original. If you've got a half, that means that the diagram is it's a reduction. And it's been reduced by what? What factor? It's half as big, yeah. And I forgot one little line up at the top here. I want to make sure I address this box right here. A scale factor of 1 means that the numerator and the denominator are the same. It means that a measurement in the diagram or in the scale, in the copy, is exactly the same as the original. Scale factor of 1. I have had the misfortune of having something like this happen. My aunt decided it would be a good idea to take a picture of the cousins. There are 3 of us, myself, my sister, and our younger cousin, for our grandmother. And she printed this thing up on canvas. She didn't intend for it to be, but she ordered a really big canvas. And the scale of us in real life versus the picture that my aunt ordered is 1-to-1. We are as big hanging on her wall as we are in real life. It is a terrifying picture. She loves it. It has never left. We are quite disappointed. So the scale of 1-to-1, a scale of 1 means the same size. My sister hates the picture. My cousin, I think it's hilarious. So scale of 4 means the diagram has been 4 times as big. An enlargement. 0.1 means your scale factor is, means your diagram is, it's reduced. And 0.1, if I convert this to a fraction, is 1/10. It means your diagram is 1/10 the original. Still could be pretty big, depending on what the original is. 2/5 is another reduction. That means for every length that is 5 long in the original, in the scale it's only 2 long. Or in the diagram it's only 2 long. And this guy here, it's an enlargement. And sometimes it's actually useful to get away from the fraction, put it back into a decimal. 3/2 is what as a decimal? 1.5, you bet. And so putting it into a decimal actually gives us an idea of how many times bigger or smaller this thing is. An enlargement that is a scale factor rather of 3/2 means it's 1.5 times bigger. 1.5 of whatever the original is your diagram. Cool, flip the page. I'm going to do an example of what this looks like and then leave you to play with a couple. So we're going to draw some images using scale factors. These are simple images, nothing ridiculous here. Nice, smooth, straight edges. I've got this little cross-looking shape here. We want to draw a scale version of this using this scale factor, 0.5 or a half. Is that an enlargement or a reduction? It's a reduction. So this thing is going to be half as big as the original. So let's draw that. What we want to do is we want to take every measurement. We want to take every measurement and we want to multiply it by the scale factor. So this guy right here has a length of 2. It doesn't matter where you start. You can start anywhere. I usually like to start like top left corner. You can start anywhere. This guy has a length of 2. So in the thing that we're going to draw, how long is that piece, the drawing going to be? Well, I'm going to take my length. I'm going to multiply the scale by the scale factor. So 2 times 0.5 is, well, what's half of 2? 1. So I'm going to need to redraw this thing so that this same side in the new one is only 1 unit long. Well, let's do this. There it is. I'll put it right there. So this side here represents that side there reduced. And I'm just going to keep going around the shape. This next line here is 1 unit long. So in my scale diagram, it's actually going to be how long? 0.5. Yeah. So we're going to go halfway down. And now our next line is a line to the right. In the original, it's 1 unit long. So in my scale diagram, how long is it going to be? Half a line. or half a unit, you bet. So it's going to go from there out into the middle of the square somewhere. Well, not somewhere, out to the middle of the square. And now we've got this side here. This side is 2 units long. So in this scale diagram, it's going to be 1. So it's going to go from the middle of one box to the middle of the other box. Oliver, stop talking to Hayden. If I have to ask you again, I will force you out onto the couches. So now this side here is 1 in the original, so it's going to be a half in the drawing. So then another one, this one's 1, so now it's going to be a half. This is 2, so now it's only going to be 1. This is 1 in the original, so it's going to be a half in the drawing. This is 1, so it's going to be a half. This is 2, so it's going to be 1. That's 1, so in the drawing it's going to be half as big. And this last side here is going to be half as big right there. So now we've got this little drawing here, and this guy is half as big in every respect as this one is here. It looks a lot smaller than half as big, but it is. It's half as big in every respect. Comments, questions, concerns? Okay, let's do another one. I'll do one more and then I'll leave you to play with some. We have the letter M. The letter M is nice. The letter M is just a bunch of straight lines. So we want to redraw this using a scale factor of 2. So is this an enlargement or a reduction? It's an enlargement. We are going to make the letter M twice as big. So it doesn't matter where we start. There are smart places and less smart places to start, but it doesn't really matter. Where do we want to start? Somebody pick a spot. Left makes a lot of sense because if I start on the left side and I start at like here, let's say that this dot right there represents this starting point right here. That means when I'm drawing this bigger version of the letter M, it's going to grow out this way from that point there. My other class, the Blog A class, said, you know what? No, we're going to start top right. But we have to make sure we started way the heck over here so that you don't grow back into the original drawing. So this is a scale factor of 2. So this first line right here in the original is 1 long. So we're going to take our measurement there. If that's a length of 1, we're going to multiply it by 2 to get the length in the scaled up version. So 1 times 2 is 2. So this line there represents that line there. Now we're coming to this guy here. These diagonal lines, for whatever reason, seem to be the hardest portion of these scale diagrams for students to do. But if you think about it in terms of the stuff we did last chapter, it's really not that difficult to do. What can you tell me about this diagonal line? It goes down 2 and over 1. It has a slope of down 2, right 1. So what the scale factor is going to do is it's going to double that whole slope. So it's going to go to the right 2 and down 4. So instead of we're not just multiplying the length, we're actually going to, this thing here has a slope of -2 over 1. It's not meant to, yeah, -2 over 1. And so what we're going to do is we're going to multiply that thing top and bottom by our scale factor. So it's going to become -4 over 2. We're going to go down 1, 2, 3, 4 over 1, 2. And we're going to put a dot there and we're going to connect those dots. Likewise, we've got another diagonal here. This one went right 1 up 2. So we're going to go right 2 up 4. And sketch it freehand as straight as you can. Unless you want to pull out a ruler, you're welcome to do that as well. Now we're up to here. This one's going to be another line that's too long. This one goes, in the original, goes down 1, 2, 3, 4. So in the diagram, it's going to go down Someone said 8. That's right. 1, 2, 3, 4, 5, 6, 7, 8. Put a dot, connect the line. Now we're going to go over 2. We're going to go up 4. And you can start making some shortcuts here. Like you can look at the original and say, look, the point at the bottom of the diagonal on the bottom one is directly below the diagonal on the top, and it's in line with the base. So I can put that right there. I can just say, I know the diagonal is going to end up down there. It's got to be in line with both that point right there, and it's got to be level with the base. So it's got to be that point there. Likewise, that point there, the top of the diagonal, is going to be 2 away just like this one was, but it's going to be on the other side. So I know that that point there is going to be a thing. And we can start shortcutting and seeing how these things end up. So I'm going to have a point there, I'm going to have a point there, and now I can just go ahead and connect the dots. I recognize that I'm going to have a diagonal here, a diagonal here, a vertical there, a horizontal there, and another vertical here. And now I've got the letter M twice as big as it was over here. Again, I think it looks a lot bigger than twice as big, but that's what it means to scale up a two-dimensional object. Comments, questions, concerns? Okay, then I want you to flip the page, and I want you to do pages 4 and 5. There's 4 drawings to do, 2 enlargements, 2 reductions, and I want you to play with those. I will give you 10 minutes. 12 minutes. At 12:30, we'll take these up on your market set, go. 4 drawings, grow them or shrink them. Okay. You. Okay, Jackson, wake up. I want you to do these 4. It would help if you did the things that we were doing too. Start on this one. Now you're doing a reduction. Yeah, page 4 and 5. What have you been doing since our class? Why do you have 2 copies of the book? Oh, I don't know. So you can clear that part up. Get to work. Give me your phone. It's out. Why don't you put it away? Doing something. The questions I assigned, you're not even on the right page. I want you to do page 4 and 5. You also didn't do any of the things that I did here. I just did 2 examples. I walked you through them, and you didn't do so. So no, I'm not going to let you have your phone. I'm going to take it from you. Yeah. Yeah. Here you go. Go ahead. Go to the washroom. Oh, hold on. Go back. Yeah. So like you take every length in the original, and you multiply by the scale factor. So what's 2 times 2.5? Yeah. So you're going to draw the top line 5 1. Start right here. Draw 5 1. Yep. Same place they've been all semester.
Yeah, which is where?
Which is right here. You can use it standing right here, yeah. Use it. Before.
Ooh, sharp banana. Tennis ball. Jackson, you want a tennis ball? Want a tennis ball? You can catch it in your mouth. Marcus, catch it in your mouth.
Hey, just get sharpen and get over here.
Wait, did someone take my paper?
Yes. No, you may not.
Damn, bro, that was so close. It's lightly captivated. Yeah, it's lightly.
Well, he's gonna say it's chocolate.
No. You can do one thing and one thing only.
And that's my drink?
No, you can take tennis ball in your mouth.
Yeah, no, I messed up a little bit. The next one I got.
Okay. So this is 2 units long. So you take however long it is. You multiply by the scale factor. You calculate for that too. Like, what's 2 times 2.5? One of those numbers. So now, starting there, the original 1. So what's 1? Right. So you're going to go down. Language. Okay. I want 80 stuff back. All of it. This is stuff. Giggle. Where's the stuff? What's the scale factor? Scale factor will tell you what to do. Oh, this was too long. This one went down to over 1. This one needs to go down to 6. So this one's actually squished tighter. And if you look here, see how this that point, all lined up. And this should log with this guy. Yes, you bet. How we doing? That's great. Yeah. Well, this is too long. So what's 2 times what? Okay. Quran. Language. Never mind. What's up? What you get? No, it's not 5. No, it's not 5 everywhere. No. You take the length, you multiply by the scale x. So this is 2. 2 times 2.5 is 5. So 1, 2, 3, 4, 5. That's great. This is only 1. So what's 1 times 2.5? 1 times 2.5. So from here, this is the top side. We're only going to go down 1, 2 and a half. Right there. You want to this one? Finish this one. Yes, sir. No, just page 4 and 5. Just there's 4 drawings I want you to do. Yeah. Did you figure out the H? Okay, go ahead. Okay. Okay, this guy is going to be huge. Okay, so here's what your first two should look like. And you guys, you can use the originals. There are things in the original that will give you a hint of what your scaled up things or scaled down things should look like. So for example, like the diagonals are still, as I said, they're tricky and they're proving to be. But things like this, like you'll notice that in the original, this point, and this point were all on the same line. So then this point, and this point should still all be level with each other. Just because you're blowing it up or shrinking it down, Oliver, what are you doing? Why? Please go put that in the recycling. Just because you're blowing it up or shrinking it down doesn't mean the picture itself gets to change. It just gets bigger or smaller. So these are what the first two look like. 1 second. Hello? Okay, so then the arrow is going to look like this. This is a reduction of a half. So everything is half as big in the arrow. So if this side, I'll start right here with this corner right here. Heading to the right, this was 1, 2, 3, 4 long. So half of 4 is 2. So in that line, it's only going to be 2. This line going up from there was 2, so it's only going to be up 1. This line went over 1, 2, 3, 4, down 1, 2, 3, 4. So we're going to go over 1, 2, down 1, 2. Same thing here. Same thing here. Same thing here. Same thing there. You just take whatever the side length is and multiply it by the scale factor. So this side is 4, half of 4 is 2. This side was 2, half of 2 is 1. And then the last one, the last one's a little bit more gross because the scale factor is a third. So we're going to pick a better place to start than we did before. I'm still going to start in that top left corner, but I'm going to deal with this straight edge here first. Gabe, let go of Andrew's stuff. Andrew, stop provoking Gabe with your pencil. The length of this side here is 1, 2, 3, 4, 5, 6. So a third of 6 is 2. So the H is going to start by being that big. This side is that side there. Now, for something like this, I'm going to be careful how I proceed here. What I could notice, I could say, okay, well, this is 2, and a third of 2 is 2/3, because 2 times 1 over 3, I put the 2 over the 1. It's like we've been multiplying fractions since September. This is going to become 2 times 1 is 2, 1 times 3 is 3. And so this next line here is going to be 2/3 of a unit long. Or I could look at this thing and say, okay, well, if that's 2, and this is 2, and this is 2, that means this whole length here needs to be 6. Which means that if the whole length is 6, and I'm reducing it by a third, that means the whole length across is only going to be 2. And so then this side here should start right here and be this vertical edge there. And so now I'm going to go over 2/3. 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 Up 2/3, down 2/3. And I'm going to get an H that looks like that. And so you need to then estimate how far along that square is 2/3 of the square. But your h should look like that. So that h is 1/3 the size of the original that was there. Questions, comments, concerns? Okay, if not, then the last thing I want you to flip the page one more time. There's one more thing we're going to take a look at today. And we're going to look at finding the scale factor using diagrams. So, sorry, what? You're good? Okay. The time is 12:37. The clock on the wall is working again, Raven. Here we go. We can find the scale factor by comparing the original and a diagram. So rather than giving you a diagram and a scale factor and having you draw, I'm going to give you the two diagrams. You got to tell me what the scale factor is. So to do that, the scale factor, as if you recall, is given by, the scale factor is equal to the scale diagram measurement divided by the original measurement. Oliver, I want your phone gone. Hayden, I want your phone gone. If I see them again, I'm taking them from you. So for all of these, I'm going to abbreviate the scale factor as SF. And it's going to be the diagram over the original. And so now all I'm going to do is fill in these fractions and simplify them where possible. So I've got two triangles here. It doesn't matter which sides I pick as long as the sides I pick are corresponding to each other. So on this guy, in my original, if I take a look at this guy down here, what side corresponds to that guy in my scaled up version? It's going to be the same one. That vertical side right there. And now I'm just going to fill in this fraction. How big is this side here? Someone said 8. How big is this side down here? It's 2. So that means my scale factor is going to be the scale diagram. That side has a length of 8 divided by that side there 2. Means my scale factor is 4. My diagram is 4 times larger than my original. And we can check it using the other sides too. Instead of using those vertical sides, let's use these two horizontal sides. The length here is still 2. The length here is still 8. So if I look at 8 over 2, if I'm using different sides now, I'm still going to get the same scale factor. Now there's a piece of added mathematical information. If you take multiple corresponding sides and they have the same scale factor, one of the things that we can say here is if the scale factors are the same everywhere in both of these or for both of these shapes, we'll go from one shape to the other for all their sides, we say these shapes are similar. So similarity in math actually has a definition. Similar doesn't mean, oh, they're kind of, sort of alike. No, similar in math means that every corresponding measurement has been blown up by the same amount. So we'll take a look at these last two. I've got 2 more to take a look at, the rectangle and these cars. What are the scale factors of the examples below? Well, I've got original is A, scale diagram is B. So I want to figure out what the scale factor is. Remember, the scale factor, SF, is equal to the diagram length divided by the original. So I just have to pick some sides, pick a side in one of them, and then find the corresponding side in the other. So this one, I'll pick this guy here, the left edge. Now these guys are oriented the same way, so the corresponding side on the original is this left edge down here. On the scale diagram, how long is it? It's 4 long. So my scale factor is going to be 4 in the scale diagram divided by, how long is that corresponding side in the original? It's 2. So 4 divided by 2 is? 4 divided by 2? It's 2. Now let's just check the other one, make sure the scale factors are the same. Let's use the bottom edge this time instead. What's this bottom length? It's 8. And this one's 4. 8 divided by 4 is 2. I have the same scale factor. So the scale factor is, this diagram is twice as big as the original. And the last one, remember the scale factor is equal to the diagram measure divided by the original length. So the scale factor here is going to be what? Well, what's the scale diagram length that we're given? Well, we're given the length of that little roof there, we're told is 3 centimeters. And this is labeled, this is the scale diagram. So that 3 is going to be up there in the numerator. This is the corresponding length in the original, so that goes in the denominator. 3 over 15 can be reduced to? Sorry? 1 over 5. Both 3 and 15 are divisible by 3, so that's going to give me a scale factor of 1/5. Which means this is a reduction, where the other two were enlargements. And that's it. That's our first lesson on this stuff. I want you to flip the page. I want you, for homework, well, you're going to finish it. You should be able to finish it in the next 18 minutes. Pages 7 and 8. It's not a lot. This page here, and if you flip the page once, this guy here. That is all. On your market, say giver.